Tonight, we're going to follow the most extraordinary biography ever written. The story of water. Not just any water, but perhaps the very molecules flowing through your body at this moment. The drops you drank today, the rain that might be falling outside your window right now. Take a deep breath and settle in. This journey will carry us across billions of years and countless miles, but we'll travel at the gentle pace of a meandering stream. There's no hurry here, no deadlines to meet, just the soft flow of knowledge, like water itself, finding its natural course through time and space. Our story begins not on Earth, but in the nuclear furnaces of stars that died long before our sun was even a glimmer in a cosmic cloud. Picture the universe as it was billions of years ago. Vast, dark, punctuated only by the brilliant glow of the first stellar giants. These weren't the orderly stars we see in tonight's sky. These were cosmic pioneers, massive and brilliant, burning through their fuel at extraordinary rates. For most of human history, we assumed water was eternal, unchanging, always present in the forms we knew. But water's true origin story is far more dramatic and ancient than anyone could have imagined. The hydrogen and oxygen that make up every water molecule have journeys that stretch back to the very beginning of time itself, woven into the grandest story the universe has to tell. Deep within these ancient stellar cores, something beautiful was happening. The intense pressure and heat, temperatures reaching tens of millions of degrees, were forging the very elements that would one day become essential to life. Imagine a cosmic foundry where the raw materials of existence were being hammered into shape, atom by atom, in the hearts of dying giants. The molecular dance. In the frigid depths of space, where temperatures hover just a few degrees above absolute zero, something remarkable began to happen. The oxygen atoms we followed in their stellar birth were about to encounter their molecular partners in one of the universe's most important partnerships. This wasn't a dramatic collision or violent reaction. Instead, it was an incredibly gentle process, almost like a cosmic slow dance played out over millions of years. The formation of water in space defies our everyday understanding of how molecules come together. On Earth, we're used to chemical reactions that happen quickly, often with heat or catalysts, to speed things along. But in the vast emptiness between stars, chemistry operates by entirely different rules. Here, in regions so cold that atoms move sluggishly and molecular interactions happen at an almost geological pace, the most fundamental partnerships in the universe can finally take place. Picture these ancient oxygen atoms, products of stellar death, drifting through the cosmic void. They've been wandering for millions of years now, part of vast molecular clouds that stretch across dozens of light years. These clouds aren't empty. They're filled with the raw materials of future stars and planets, a thin soup of atoms and simple molecules floating in the darkness. And the most abundant ingredient in this cosmic recipe is hydrogen, the universe's simplest element, created not in stellar cores, but in the first few minutes after the Big Bang itself. When an oxygen atom encounters hydrogen in these frigid conditions, something beautiful happens. Oxygen, with its strong attraction for electrons, draws hydrogen atoms close like a gentle magnet. The process is so subtle that if you could watch it happen, it would seem almost like the atoms are negotiating, finding the perfect arrangement through quantum mechanical forces we're only beginning to understand. Two hydrogen atoms find their way to a single oxygen, and together they form what chemists call covalent bonds, partnerships where electrons are shared between atoms, creating a stable molecular family. But this isn't just any random three-atom arrangement. The way these atoms organize themselves creates something almost magical in its precision and beauty. Hydrogen, the universe's simplest and most abundant element, was being transformed through nuclear fusion. This wasn't a gentle process. It required conditions so extreme they're almost impossible to comprehend. At the stellar core, pressures were millions of times greater than anything we experience on Earth, and temperatures hot enough to strip electrons from atoms entirely. Under these unimaginable forces, hydrogen nuclei overcame their natural electrical repulsion, like forcing two powerful magnets together and joined in nuclear fusion, creating helium and releasing tremendous energy in the process. But the stellar alchemy didn't stop there. In the most massive stars, those cosmic giants that burned bright and fast, fusion continued beyond helium in a series of increasingly complex nuclear reactions. Carbon formed from the collision of three helium nuclei in a process so delicate it seems almost miraculous. From carbon came neon, then magnesium, then silicon, each element built upon the last in a cosmic assembly line of atomic construction that transformed simple hydrogen into the building blocks of complexity. And crucially for our story, oxygen was born in these stellar foundries. Created when carbon nuclei fused with helium in a process called helium burning, oxygen emerged as one of the most abundant heavy elements in the universe. Every oxygen atom that would later become part of a water molecule was literally forged in the belly of a dying star. Created in conditions of unimaginable violence and beauty. Think about that for a moment. The oxygen in your lungs right now, the oxygen that makes up 8/9 of every water molecule's mass, carries with it the memory of that stellar crucible where it was born. Each atom spent millions of years in the core of a star, participating in the nuclear reactions that kept that ancient giant shining across the cosmos. When these stellar titans reached the end of their lives, they didn't simply fade away quietly like smaller stars do. They had grown too massive to support themselves, and in a matter of seconds, they collapsed under their own gravity and then exploded in spectacular supernovas, events so violent they briefly outshone entire galaxies. These cosmic cataclysms were more than just spectacular light shows. They were the universe's way of distributing the elements necessary for complexity, planets, and life. The explosion scattered the newly created elements across vast regions of space, sending shockwaves rippling through the cosmic medium at thousands of kilometers per second. These expanding shells of hot gas, enriched with heavy elements, seeded enormous volumes of space with the raw materials needed for the next generation of stars and planets. Picture these oxygen atoms, newly forged and now free, riding the blast wave of their stellar parents' death. They join the slowly expanding shells of gas and dust blown outward by the supernova's shockwave, mixing with hydrogen that had existed since the universe's first few minutes. For millions of years, these atoms wandered through the cosmos, part of vast molecular clouds that drifted between the stars like cosmic tumbleweeds, slowly cooling and condensing in the cold depths of space. These weren't barren regions of emptiness despite what we might imagine about the vacuum of space. Instead, They were vast stellar nurseries, where gravity slowly gathered the scattered elements into dense clumps that would eventually become the birth sites of new stars and planetary systems. The oxygen atoms that had begun their journey in stellar cores now found themselves part of these molecular clouds, waiting patiently for the next chapter in their cosmic story. What's remarkable about this process is how it connects the smallest scales of matter to the largest structures in the universe. The quantum mechanical processes happening inside individual atomic nuclei, governed by the fundamental forces of nature, were literally building the chemical complexity that would one day make planets, oceans, and life possible. Every supernova was both an ending and a beginning, the death of one star, but the seeding of countless future worlds. And so, billions of years before Earth existed, the atoms that would eventually form its oceans were already beginning their slow journey toward our corner of the galaxy. They would travel for eons through the interstellar medium, sometimes gathering into dense molecular clouds, sometimes dispersing into the cosmic void. Always moving, always cycling through the great chemical processes that govern the universe. The oxygen atom, being larger and more electronegative than hydrogen, doesn't share the electrons equally. Instead, it pulls them slightly closer to itself, creating a subtle electrical imbalance that gives the water molecule its unique personality. Picture a tiny Mickey Mouse head floating in space. The oxygen forms the large round face, with two hydrogen atoms creating the ears at an angle of precisely 104.5 degrees. This geometry isn't arbitrary. It's the result of electron clouds pushing and pulling against each other until they find the perfect quantum mechanical balance. This bent shape is crucial to everything that follows in our story. If water molecules were linear, with both hydrogens on opposite sides of the oxygen like a tiny barbell, water would be a completely different substance. It might be a gas at room temperature, incapable of forming the complex networks that make life possible. But nature, through the fundamental laws of quantum mechanics, has given water its characteristic angle, and that geometry shapes every property that makes this molecule so special. The electrical imbalance created by water's bent geometry means that water molecules are naturally attracted to each other. The slightly positive hydrogen end of one molecule reaches toward the slightly negative oxygen end of another, creating what we call hydrogen bonds. These aren't as strong as the covalent bonds that hold each water molecule together internally, but they're persistent and numerous, creating a network of molecular attractions that gives water many of its remarkable properties. Imagine billions upon billions of these tiny molecular dancers constantly moving, constantly reaching for each other, constantly forming and breaking these gentle connections. It's a ballet that's been performing since these molecules first formed in the depths of space, and it's happening right now in every glass of water, every raindrop, every cell in your body. Each water molecule spends its existence in this constant dance of attraction and separation, never alone, always part of a larger molecular community. In the cold depths of space, these newly formed water molecules began to accumulate in the dense cores of molecular clouds. Here, shielded from the harsh radiation of nearby stars, protected by layers of cosmic dust, water could survive and even multiply. Other molecules joined the mix: carbon monoxide, ammonia, methane, creating a chemical diversity that would later seed the formation of planets and eventually life itself. This is how water's story truly begins, not with rain or rivers or oceans, but with the nuclear fires of ancient stars and the violent beauty of cosmic explosions. Every drop of water on Earth is a messenger from this ancient past, carrying within its molecular structure the memory of stellar birth and death, of cosmic recycling on the grandest possible scale. In the cold depths of space, these oxygen atoms were about to encounter their molecular partners, and begin the next chapter of their remarkable journey. But water molecules in space don't behave exactly as they do on Earth. In the extreme cold of interstellar space, they often freeze onto tiny grains of dust, forming icy mantles that coat these microscopic particles. Picture these dust grains as cosmic snowflakes, each one carrying a cargo of frozen water and other simple molecules. These ice-coated grains would play a crucial role in the next chapter of our story, serving as both the building blocks of larger objects and the delivery vehicles that would eventually bring water to worlds like Earth. The hydrogen bonding that makes water so special also means that even in the vacuum of space, water molecules tend to stick together, forming small clusters and networks. These aren't like the ice we know. Instead, they're more like loose associations of molecules held together by those gentle hydrogen bonds, but still able to move and rearrange themselves as conditions change. What's remarkable about this process is how universal it is. Wherever you find hydrogen and oxygen in the right conditions, water forms naturally. It's not a rare or exotic compound requiring special circumstances. It's an inevitable consequence of the way these elements interact. Astronomers have detected water vapor in star-forming regions throughout our galaxy and beyond, a testament to the fundamental nature of this molecular partnership. The water molecules forming in these ancient molecular clouds weren't destined to remain in space forever. Gravity was already beginning to work its slow magic, pulling the gas and dust together into denser and denser regions. Some of these concentrations would become new stars, their internal heat vaporizing the water and sending it back into space, but others would become something different, the raw material for planetary systems, where water could finally find more permanent homes. As we follow these water molecules on their cosmic journey, it's worth pausing to appreciate the elegant simplicity of what we've witnessed. 3 atoms, 1 oxygen born in a stellar furnace, 2 hydrogens created in the universe's first moments, coming together in the cold depths of space to form a molecule that would become the foundation for everything we recognize as life. No complex machinery, no intelligent design, just the fundamental forces of nature playing out their eternal patterns in the darkness between the stars. This is chemistry at its most basic and most profound. The idea that simple rules, followed consistently across space and time, can create complexity and beauty beyond imagination. Every water molecule that would eventually find its way to Earth began this way, as a chance encounter in the cosmic cold, a moment when 3 atoms discovered they could create something greater than the sum of their parts. The stage was now set for the next act in our story. These water molecules, along with countless others forming throughout the galaxy, were about to be swept up in one of the most dramatic events in cosmic history, the formation of our solar system itself. Our water molecules found themselves in different regions of this collapsing disk, and their fate would depend entirely on where they ended up. Near the center, where the proto-sun was forming, temperatures soared to thousands of degrees. Any water molecules that ventured too close to this region were instantly vaporized, their hydrogen and oxygen atoms torn apart and scattered by the intense heat and radiation. But farther out in the disk, beyond what astronomers call the snow line, conditions were very different. Here, roughly where the asteroid belt sits today, temperatures were cold enough for water to freeze into ice. This invisible boundary would prove crucial to the architecture of our solar system, determining which worlds would be rocky and dry, and which would be rich in water and other volatile compounds. The water molecules that found themselves beyond the snow line began to stick to tiny particles of dust and rock, forming the icy building blocks that would eventually become comets, asteroids, and the cores of giant planets. These weren't large objects yet. Most were no bigger than pebbles or small rocks. But they were numerous beyond imagination, and they carried within their frozen structure the water that would one day fill Earth's oceans. Meanwhile, closer to the forming sun, in the hot inner regions of the disk, the rocky planets were beginning to take shape. Mercury, Venus, Earth, and Mars formed from the collision and accretion of countless rocky and metallic particles. But they were largely dry worlds, their water having been vaporized by the young sun's intense heat and radiation. Earth, in particular, began its existence as a molten ball of rock, constantly bombarded by debris left over from the solar system's formation. Any water that might have been present on Earth's surface during this violent period would have quickly boiled away into space. The planet's early atmosphere, if it had one at all, was probably swept away by the solar wind. Streams of charged particles flowing outward from the young sun. For hundreds of millions of years, Earth remained a harsh, waterless world. Nothing like the blue marble we know today. Birth of a solar system. The water molecules we've been following through space were about to become part of something extraordinary. The birth of our own solar system. But this wasn't a sudden dramatic event. Instead, it was a slow-motion collapse that took millions of years to unfold. A cosmic dance of gravity, rotation, and chemistry that would eventually create the stage for life itself. About 4.6 billion years ago, our water molecules found themselves part of a vast molecular cloud, drifting through space near what would become our corner of the galaxy. This cloud was enormous, perhaps 50 light-years across, and filled with the debris of countless stellar generations. Hydrogen and helium dominated its composition, but scattered throughout were the heavier elements forged in ancient stellar cores. Carbon, nitrogen, oxygen, and all the other building blocks of complexity. Something disturbed this cloud's peaceful equilibrium. Perhaps it was the shockwave from a nearby supernova, or the gravitational influence of a passing star cluster. Whatever the trigger, it set in motion a cascade of events that would transform a diffuse cloud of gas and dust into a family of planets orbiting a young star. The cloud began to contract under its own gravity, slowly at first, then with increasing speed as the gravitational attraction of its constituent parts grew stronger. As the cloud collapsed, it began to spin. This wasn't by choice, it was a consequence of the conservation of angular momentum, the same principle that causes a figure skater to spin faster when she pulls her arms close to her body. The cloud flattened into a disk, with most of the mass concentrating toward the center, where temperatures and pressures began to climb toward the point where nuclear fusion could ignite. But water hadn't abandoned Earth entirely. It was simply waiting its turn, stored safely in the cold outer regions of the solar system in the form of comets and water-rich asteroids. These objects had formed beyond the snow line where ice was stable, and they contained vast amounts of frozen water, along with other volatile compounds like carbon dioxide and methane. Gradually, as the solar system settled into its current configuration, some of these icy bodies began to make their way toward the inner planets. Gravitational interactions with the giant planets, Jupiter, Saturn, Uranus and Neptune, would occasionally perturb the orbits of comets and asteroids, sending them on long elliptical journeys that sometimes brought them into the inner solar system. When these objects collided with the young Earth, they delivered their cargo of ice and rock to our planet's surface. But Earth was still hot, its surface molten from the constant bombardment and the heat generated by gravitational compression. The ice vaporized instantly upon impact, adding water vapor to the growing atmosphere. For millions of years, this process continued, ice-bearing objects striking Earth and gradually building up the water content of the atmosphere. Slowly, very slowly, Earth began to cool. The bombardment of large objects decreased as the solar system swept up most of the leftover debris from its formation. Without the constant input of heat from impacts, and with the help of an atmosphere that was growing thicker and more complex, Earth's surface temperature began to drop toward the point where liquid water could exist. The transition wasn't sudden. For perhaps millions of years, Earth existed in a state where water vapor filled the atmosphere, creating a thick, steamy blanket around the planet. The atmospheric pressure was enormous, and temperatures remained well above the boiling point of water. But as more heat radiated away into space and Earth continued to cool, a critical threshold was finally crossed. Somewhere around 4 billion years ago, the surface temperature dropped below 100 degrees Celsius, the boiling point of water at Earth's atmospheric pressure. For the first time in our planet's history, water could exist as a liquid on the surface. What happened next was one of the most dramatic weather events in Earth's history. A rainfall that lasted for millions of years. The water vapor that had been suspended in the atmosphere for so long began to condense into droplets. Clouds formed, grew thick and heavy, and released their cargo in torrential downpours that dwarfed anything we can imagine today. This wasn't gentle spring rain or even the most violent thunderstorm. This was a planetary deluge that continued for geological ages. Our water molecules, which had begun their journey in the hearts of ancient stars, traveled through the cold of interstellar space, survived the formation of the solar system, and endured the violence of planetary bombardment, finally found themselves falling as rain toward Earth's surface. Drop by drop, they began to collect in the low places, the basins and depressions that would become our first oceans. But this early Earth was nothing like the world we know. The atmosphere was toxic, filled with volcanic gases and devoid of free oxygen. The oceans were hot and acidic, more like a chemical soup than the blue waters we know today. Lightning crackled constantly through the thick atmosphere, and volcanic activity was far more intense than anything we see in the modern world. Yet for all its hostility, this early Earth had achieved something remarkable. It had become a world where liquid water could exist at the surface, where the fundamental chemistry of life could begin to experiment with new possibilities. The water molecules that had traveled so far and endured so much were finally home, ready to begin the next chapter of their extraordinary story. In these ancient oceans, surrounded by conditions that would be lethal to most life as we know it, water was about to play its most important role yet. It would become the medium in which the first tentative steps toward life would take place. The protective environment where simple chemistry would gradually give way to the complex molecular machinery of living systems. The stage was set for one of the most important transformations in the history of our planet: the emergence of life itself from the patient, nurturing embrace of liquid water. The cradle of life. In the ancient oceans that covered much of the early Earth, our water molecules were about to witness and participate in one of the most extraordinary events in the history of the universe: the emergence of life. But this wasn't a sudden spark or dramatic moment of creation. Instead, it was a gradual awakening that took hundreds of millions of years. A slow dance of chemistry and possibility played out in the protective embrace of liquid water. Picture these primordial seas as they existed nearly 4 billion years ago. They bore little resemblance to the blue waters we know today. Instead, they were a rich chemical soup, tinted perhaps with iron that gave them rusty hues, or darkened by organic compounds raining down from space. The water itself was hot, much warmer than any modern ocean, and it was filled with dissolved minerals and gases from the planet's restless interior. Volcanic vents dotted the sea floor, belching forth streams of superheated water loaded with hydrogen sulfide, methane, and other chemicals that would be toxic to most life today. But in this ancient world, these seemingly hostile conditions were actually perfect for the kind of chemistry that would eventually lead to life. The vents provided energy, the oceans provided a stable medium, and time provided the opportunity for countless molecular experiments. Water played multiple crucial roles in this grand chemical experiment. First, and most importantly, it served as the universal solvent, the medium in which all other molecules could interact. Unlike other liquids that might have existed on early Earth, water had the unique ability to dissolve both salts and organic compounds, creating a three-dimensional space where chemistry could happen in ways that would be impossible in the gas phase or on solid surfaces. But water was more than just a passive container for chemical reactions. Its unique properties actively facilitated the formation of complex molecules. The hydrogen bonds that give water its special characteristics created a constantly shifting network of molecular connections, a liquid structure that could guide and influence how other molecules came together. In the presence of water, organic compounds could fold into precise shapes, form stable associations with each other, and explore new configurations that might have been impossible in any other environment. The early oceans were also a protective shield against the harsh conditions that prevailed on early Earth's surface. Above the water, the atmosphere contained no oxygen and provided little protection from the sun's ultraviolet radiation, which could destroy complex organic molecules in seconds. But even a few feet below the surface, water filtered out the most damaging wavelengths, creating a zone where delicate chemistry could proceed at its own pace. In this underwater sanctuary, the building blocks of life began their tentative experiments with complexity. simple organic molecules, carbon-based compounds that had either formed on Earth through chemical processes or arrived from space on comets and meteorites, began to interact with each other in increasingly sophisticated ways. Amino acids, the building blocks of proteins, formed long chains. Nucleotides, the components of DNA and RNA, began to link together into primitive genetic molecules. Water facilitated all of these processes through its role as both solvent and facilitator. The polar nature of water molecules meant they could surround and stabilize charged or polar groups in organic molecules, while their non-polar regions could interact with the hydrophobic parts of these same molecules. This created a kind of molecular choreography, where water helped guide organic compounds into the precise arrangements needed for biological function. One of the most crucial steps in this process was the formation of cell membranes, the barriers that would separate the interior of the first cells from their external environment. These membranes were made of molecules called phospholipids, which had a unique property. One end was attracted to water, hydrophilic, while the other end repelled water, hydrophobic. In the presence of water, these molecules spontaneously arranged themselves into double layers, with their water-loving heads facing outward toward the aqueous environment and their water-hating tails facing inward away from the water. This self-assembly process was remarkable in its simplicity and elegance. Water didn't just allow it to happen, water drove it to happen. The hydrogen bonding network of liquid water essentially excluded the hydrophobic tails of the phospholipids, forcing them to cluster together and form the core of what would become the first cell membranes. In this way, water itself played a role in creating the fundamental boundary between life and non-life, the membrane that would define the first living cells. Inside these primitive cellular compartments, water continued its nurturing role. It provided the medium in which the first metabolic reactions could take place, the chemical processes that would allow these early life forms to extract energy from their environment and use it to build more complex molecules. Water's ability to participate in chemical reactions through processes like hydrolysis, breaking bonds by adding water, and dehydration synthesis, forming bonds by removing water, made it an active participant in the chemistry of life. But perhaps water's most important contribution to early life was its role in the development of information storage and transfer systems. The first genetic molecules, probably RNA rather than DNA, could only function properly in an aqueous environment. Water stabilized their complex three-dimensional structures, allowed them to interact with other molecules in precise ways, and provided the medium in which they could replicate themselves. This replication process was crucial because it marked the transition from chemistry to biology. For the first time in Earth's history, molecular systems existed that could make copies of themselves, passing information from one generation to the next. These weren't yet true cells. They were more like complex chemical networks suspended in water. But they possessed the fundamental property that defines life, the ability to reproduce and evolve. The early evolution of life was intimately tied to water's properties. Natural selection favored molecular systems that could best exploit water's unique characteristics. Systems that could efficiently use water as a solvent, that could form stable associations in aqueous environments, and that could regulate their internal water content, gradually outcompeted those that couldn't. Over hundreds of millions of years, these early life forms diversified and became more complex. Some learned to harness chemical energy from the hot vents on the ocean floor. Others developed ways to capture and use the faint sunlight that penetrated the upper layers of the ocean. All of them remained dependent on liquid water for their survival and function. One group of early organisms made a discovery that would change the world forever. They learned how to use sunlight not just as an energy source, but as a way to split water molecules themselves. This process, which we now call photosynthesis, used light energy to break the bonds in water, separating hydrogen and oxygen. The hydrogen was used to build organic compounds, while the oxygen was released as a waste product. At first, this oxygen was quickly absorbed by dissolved iron in the oceans, forming the banded iron formations we can still see in ancient rocks today. But gradually, over hundreds of millions of years, the oxygen began to accumulate. The oceans became saturated with it, and eventually, oxygen gas began to bubble up into the atmosphere. This accumulation of oxygen was perhaps the most dramatic environmental change in Earth's history. To most of the life forms that existed at the time, oxygen was actually toxic, a highly reactive gas that could damage the delicate organic molecules they depended on. Many species went extinct, unable to cope with this new, oxygenated world. But some organisms adapted. They developed biochemical systems that could not only tolerate oxygen, but actually use it as a powerful source of energy. These oxygen-breathing organisms could extract far more energy from their food than their anaerobic predecessors, giving them a tremendous advantage. They multiplied and diversified, eventually giving rise to the complex, multicellular life forms we see today. The Great Circulation. As life began to flourish in Earth's ancient oceans, our water molecules were about to discover something extraordinary. They weren't destined to remain forever in those primordial seas. Instead, they were about to become part of the greatest circulation system ever devised, a planetary-scale dance that would connect every corner of Earth and every form of life that would ever exist. The sun, that same nuclear furnace that had created the heavy elements in our water molecules billions of years earlier, was now sending its energy across the 93 million miles of space to Earth's surface. When those photons struck the ocean where our water molecules floated, something beautifully simple yet profound began to happen. The energy from those ancient stellar fires was transferred to our water molecules, causing them to vibrate more and more vigorously. You can imagine this process happening right now. If you picture the surface of any body of water on a sunny day, individual molecules, energized by the sun's warmth, begin to move faster and faster until they break free from the gentle grip of their neighboring molecules. In a process so gradual, it's almost imperceptible, they rise into the atmosphere as invisible vapor, carrying with them the memory of the ocean depths and the story of their cosmic birth. But this evaporation wasn't random or chaotic. Our water molecules found themselves part of an elegant system driven by the same physical laws that governed the nuclear reactions in stars. As warm, moist air rises, it expands and cools. As it cools, those excited water molecules begin to slow down, drawing closer together once again. They seek out tiny particles of dust or salt, microscopic remnants of ancient rocks, or perhaps even cosmic dust from space, and use them as gathering points, condensation nuclei, around which they can reassemble into droplets. Other molecules would join streams and rivers, beginning one of nature's most joyful expressions, the downstream journey toward the sea. Along the way, they would witness the emergence of complex life. They would nourish the first plants to colonize the land, participate in the photosynthesis that would transform Earth's atmosphere, and become part of the bodies of the first animals to venture onto dry land. This circulation system, the hydrologic cycle, became far more than just the movement of water. It became the planet's circulatory system, its bloodstream, carrying nutrients from mountains to valleys, from continents to oceans. Our water molecules were no longer just participants in life. They had become life's delivery system, its highway, its most essential ingredient. Consider the elegance of this system. The same energy that forged our water molecules in ancient stars now drives their circulation around the planet. The same physical properties that allowed them to form in the cold of space, their ability to exist as solid, liquid, and gas at Earth's temperatures, now allows them to cycle endlessly between ocean, atmosphere, land, and back again. As our molecules continued their circulation, they began to encounter increasingly complex life forms. They might be absorbed by a fern, travel through its vascular system, and be released again through its leaves. They might form part of an early amphibian's bloodstream, carrying oxygen and nutrients to cells that were themselves mostly water. They participated in every biological process, from the simplest chemical reactions to the most complex behaviors of evolving organisms. Through this great circulation, our water molecules were becoming historians of Earth itself. In their endless journey, they were connecting every environment, every ecosystem, every form of life. A molecule that had once floated in an ancient sea might later fall as rain on the first flowers, flow through the roots of the first trees, or become part of the first drops of morning dew that early mammals would drink. High in the atmosphere, supported by columns of rising air, our water molecules helped form clouds. These aren't the solid, substantial structures they appear to be from the ground. Instead, they're gossamer collections of countless tiny droplets, each one a sphere of water molecules held together by those same hydrogen bonds we explored earlier. Suspended in air so thin that a cloud weighing millions of tons can float as effortlessly as a feather. The clouds became vehicles for our water molecules' first great journey across the planet's surface. Carried by winds that are themselves driven by the sun's uneven heating of Earth's surface, our molecules found themselves traveling vast distances. They might drift across entire continents, their cloud ships sailing through skies that early life forms below could barely imagine. When conditions were right, when the droplets grew large enough, or when the air could no longer hold all that moisture, gravity would gently call our water molecules back to Earth's surface. But now they might fall as rain onto land that had never known liquid water, onto the first tentative forests, or into rivers that would carry them on yet another phase of their endless journey. Some of our water molecules might soak into soil, beginning a patient underground journey that could last thousands of years. Moving slowly through rock and sediment, they would travel through aquifers, underground rivers and lakes that exist in a darkness beneath our feet. Here, they might remain for millennia, part of vast underground reservoirs that serve as Earth's deep memory, storing water from ancient rains and releasing it slowly through springs that have bubbled up for countless generations.
Through all of these changes, from the first simple chemical networks to the complex organisms that would eventually evolve into plants, animals, and fungi, water remained the constant, the medium that made life possible. Every metabolic reaction, every genetic process, every interaction between cells happened in the context of water's unique properties. The water molecules we've been following through their cosmic journey were now integral parts of living systems, flowing through cell membranes, participating in chemical reactions, and helping to maintain the delicate balance that keeps life functioning. They had found their ultimate purpose, becoming not just witnesses to the story of life on Earth, but essential participants in it. Yet their journey was far from over. As life evolved and diversified, water would take on new roles, new functions, and new ways of connecting the living and non-living worlds. The stage was set for the next great chapter in water's story, its role in shaping the planet's climate and weather systems, and in connecting all life through the endless cycle of evaporation and precipitation that we know today.